Hello, welcome to Anson Griffin's occasional series of YouTube tutorials. You've just looked at, or you should have just looked at, the order method, and now we're going to look at an improved method of solving a first order differential equation, which is Runge-Kutta. So, this is an improved method. If you remember, in the order method, we only had one tangent plane and we're dividing it up, and the Runge-Kutta is a weighted solution of 4 different tangent planes, and the weighted solution is there, and the formulas are there, but we're going to do a worked example just to give you some idea of what's going on. So remember, Runge-Kutta should give us much better approximations, smaller residual, smaller error than the other method. That's just briefly how to write the differential equation. That shouldn't be there really, and here's the one we're going to look at. So we have this heat loss problem, probably for mechanical engineers and specifically, and you have a ball at 1200, so a sphere, 4 over 3 pi r cubed, and then you want to let it cool down to 300k. Heat loss only due to radiation, blah blah blah. Formula has been established, so remember units are Kelvin, and we're going to go at find the temperature at 448 seconds. So it's fairly slow to do it by hand, so we're only going to do 2 steps. We're going to do 0, 240, 480. Okay. As you've probably guessed already, the more steps you take, the better the answer, but we just due to, shall we say, time constraints here on YouTube. So there's our differential equation. There we have it written in as a function, and there's the important thing: my new value equals my O value plus the weighted slopes here by h, which is our time slice or our time interval, which in this case is 240 seconds. Very crude, but just the h, I mean, is very crude. The method is quite refined. If I could just get my mouse to go. Okay, sorry, don't know what happened there. Okay, so there we are. So we want to do step 1. So we want to get our first slope. From the first slope we get the second slope. From the sorry, mouse is gone. We get the first slope. The first slope enables us to get the second slope. The second slope enables us to get the third slope. The third slope enables us to get the fourth slope, and then from that we get. So how do we get the first slope? So it's the f of T0 at the temperature. So that's 0 and 1200. So it's 2.0. There's the constant, the multiplying factor. There's the temperature, theta to the 4. So that's what's our initial. That's 1200 to the 4 minus 81 by 10 to the 8, and that gives us a number. So that is our first slope. K2 now is a function of T0. That's times 0 and a half h. So that's a half of 240. And so and over here we have t to 0 plus a half k1h, so we're using the first slope. So times 0 is 0, half h is a half of 240, because remember going up in jumps to 240, comma, the initial temperature 1200, a half k1h, a half 4 minus 4.5579 by h, which is our time slice, which is 240. Do all the maths, you get minus 0.38. From K3, or from K2 you get to A3, so it's the same as again, 1200 plus a half times 240, comma, 1200 plus a half K2, there we have it from just there, by 240, do all the numbers, you get minus 3.8954. K4, we get K4 from K3, same as before, T0 plus H, so that's 0 plus 240, comma, then theta 0 1200 K3 minus 3.8954 by H 240. Do all the maths, you get that. Remember, our temperature at 240 is our temperature at theta 0, which is our temperature 0, which is 1200, plus 1/6 of these weighted averages by H, do all the numbers, minus 675.65, and so the approximate temperature 240 is 675.65 Kelvin. Now we have θ1, and θ1 is going to give us θ2. So we get K1, so it's the F of T1 θ1, so our T1 now is 240, θ1 is the answer we've just got, 675. Bang it in, minus, just put up the formula there, minus 2.20 by the temperature. What's the temperature at 240? 675 to the 4, minus 81 by 10 to the 8, and we get minus 0.44. K2, slow down now, his answer is T1, that's 240, plus a half H, that's a half of 240, which is 120. Temperature at θ1, 675, plus a half times 240 by K1, which is there. We get minus 0.31. From K2 we go to K3. K3 is T1 plus a half H, so that is θ1, which is time 1 is 240. A half H is a half of 240, comma, temperature at there, we just computed 675, a half of K2H. K2 is there, so that drops in there. Do all the numbers, we get that. If we go from K3 to K4, same as before, T1 plus H, so that's 240 plus 240. We're at the end. θ1, we've got up there, 675, drop that in there. K3H, dunk, bang it all out, we get K4. θ2 equals θ1 plus 1/6 the weights, you get 594.91. So our approximate answer is 594.91 K at 480 seconds. The exact solution is 674.57 K, so we're a good bit out. And there I have a slide done of some different methods. Now you can see here that if you just did it in one step, that's 480. The error is, well, atrocious. We're getting minus temperatures. There's our 240, and we have a 120. So you can see here that when we're going in just one step, it's atrocious. 2 steps, it isn't bad, and 4 steps is better, and then 8 steps is better again, and at 16 steps is better again. So we have here a slide. Here's our error, 113%, 240, 8%, not bad, 120, a step size of 120, that would be 4 slices, that would be 0.21%, a step size of 60, so that's 8, you've divided it 8 ways, it's 0.005%, and 30 into 480, that's 16 slices, and well, it's as good as makes no difference. Okay, so a bit of a pain to do this by hand. Excel, well, less painful, and then MATLAB, just a joke. Well, what I mean by a joke, it's extremely easy once you be able to write the function. Okay, so, and there's just another way of looking at the things we've just got about the temperature. Okay, so thanks very much for your attention, and I hope I haven't gone too fast. By the way, these notes will be supplied to you in class. Okay, so thanks very much. Bye.